Hey folks, I understand that I screwed up on the screencast the other day and didn't talk about the impact that concentration of the reactants has on the reaction rate of something. Sorry about that. I just hit the microphone. So let me just quickly toss this into here so you understand what's happening. So this is a pretty straightforward concept here. As you can see here in sort of situation A versus situation B, if I increase the concentration of the reactants, then there's a greater chance that you're going to have more collisions. And if you have more collisions, then there's a greater chance that those are going to be the kind of collisions that lead to the reaction. So they'll be effective collisions. So it's just a probability situation here. When you increase the concentration, that you'll have an increase in the reaction rate because of the increase in the number of good collisions. Okay, so let's move on to the rest of the screencast that has to do with equilibrium, chemical equilibrium. So up to this point, we haven't really thought of a reaction as being anything other than a set of reactants moving to a set of products. And we just assumed that if you have a set of reactants and if you give it enough time or energy or high enough concentration or all those things that affect reaction rate, that eventually it will move towards the products and we'll be finished. We'll have no more reactants and we'll have all the products that we're going to have from those reactants. The reality is, though, that not all reactions do this. So we have that type of reaction, and I'll call that reaction type number 1, which is where all reactants convert into products. But we also have another type of reaction that exists out there where some of the reactants convert to products, but not all. And in this case, we reach a point where there is some reactant and some product. This all sounds sort of weird, so let's talk about some examples. And I'm going to show these examples in class probably tomorrow. And the first one is an example of the number 1 type of reaction where everything that is a reactant gets converted into a product. So here we have when you combine HCl with water, you produce a whole bunch of chloride ions and hydronium ions. Now, the hydronium ion isn't something that you've seen. I'm not going to talk too much about this right now, but just understand that that's when you combine, when something is an acid and you combine it with water, you form hydronium ions. And a lot of these ions are produced, these Cl- and H3O plus ions. And in fact, there is going to be no more hydrochloric acid left, and there might be some water, frankly, because there's going to be in a lot of water. But all the hydrochloric acid is going to be consumed and converted into these 2 ions. And with a second reaction here, I show that there's something called acetic acid. So HCl, you all know, is hydrochloric acid. Acetic acid, also an acid, is going to combine with water, and it forms the acetate ion, which is this dude right here, and also the hydronium ion, just as we saw in the first reaction, reaction number 1. So you would think that these would basically be reactions that behave in the same way. But the reality is that the acetic acid doesn't get completely consumed, and in fact, you reach a point of what's called equilibrium. So I actually need to include an arrow going backwards towards the reactants. So in this case, you would not expect to have the same number of ions produced in the second reaction as you would in the first reaction because some of it slightly shifts backwards towards the reactant sides. And in fact, because of this, I can just as easily write this reaction in the opposite direction and have it be equally valid. So let's say for a moment I get rid of this little red arrow here, and if we know this is a reaction that goes to equilibrium, that means it does go from the products back to the reactants, like this. And in this case, as I said, they're both valid, being able to go in either direction. All right, so the key here is that since these are reversible reactions, at some point we reach a state where we have a certain amount of reactant and we have a certain amount of products. Now that doesn't mean we have 50-50. That's something that's important for you to keep in mind. But it does mean that we don't completely lose our reactants in favor of only products. And when you reach this state, we do call it that it's in chemical equilibrium. So if we were to define this concept of chemical equilibrium in words, we would say that when you're in equilibrium, the reactants are forming products at the same rate as the products are forming reactants. It's a little odd because it becomes a bit arbitrary what you call a reactant and what you call a product in these situations. So by convention, if it's something that we see on the left side of the equation, we call it a reactant, and if it's something on the right side of the equation, we call it a product. But since they can switch, then you understand that they could assume either role. Another very important concept to understand here is that once equilibrium has been reached, that doesn't necessarily mean, or doesn't mean, that the reaction stops. Okay? In the same way that, think of this as in sort of a hockey metaphor here, you always need to have 10 players on the ice. If we exclude that penalties happen, you need to have 10 players on the ice. So that's an equilibrium, 5 per side. But that doesn't mean you're going to have the same 10 players on the ice at any one time. If one player leaves the ice, another needs to come on to make sure that you still have 10 players on the ice. So there's constant subbing in and out and constant motion that's going on. So it's a dynamic equilibrium that exists here when a reaction reaches that state. So let's take a look at an example of something that's not in the realm of acids forming. In this case, we're going to look at the formation of smog. And again, this is something that I'm going to show you guys in class because it's pretty cool. I'm not going to show it immediately because I'm going to wait till we start talking about something called Le Chatelier's rule. But it is something that, oh shoot, somebody's knocking on my door. Hold on. Oh, so I left for about 20 minutes. Smog. Okay, I think I'm just giving an example of equilibrium, an equilibrium reaction here. So we have, whoops, where's my, hold on a sec. We have a reaction. It's a pretty simple looking reaction here. 2NO2, nitrogen dioxide, gas. And since it's an equilibrium reaction, I'm going to show the arrow going in both directions. Forms dinitrogen tetroxide, which is also a gas. You should know, however, that the nitrogen dioxide is actually the dreaded smog, whereas the dinitrogen tetroxide is actually a fairly harmless gas. Clearly, we don't really want to have smog around. Smog isn't just ugly, but it actually can be harmful to human beings. So let's take a look at a situation where we start off with 100% of the smog, the NO2, and see what happens over time. So I'm going to have you draw out a table. So what we're going to do here is we're going to measure the amount of NO2 versus the amount of N2O4 over 7 time periods, and we're going to be able to measure the number of moles of each of the gas as the reaction, this one up here, takes place. You can see here that initially we start off with 100% of the smog, the N2O2, and 0 of the N2O4. And then after some period of time, the amount of NO2 drops and the amount of N2O4 starts to go up from 0 to having some N2O4. And you can see that this trend continues. And notably that the amount of N2O4 now has exceeded the amount of NO2. But then you can see in 5, 6, and 7 time periods, we don't have any change. So you can tell then somewhere between 4 and 5, we reached a point of equilibrium where we have the amounts don't change. Now notice that the amounts are different. So equilibrium doesn't mean that they're equal to each other. It means they've reached some sort of balance. Now, the important thing to do here too is to look and see what would happen if we graphed this exact data set. So you can see here I have a set of axes, and what we have over here is the number of moles of the substance, and we have here the time. And if I were simply to take all this data and plot each one of the points on here, so you could see here, for example, if I go for this first line of data where I have 0.0500 moles to 0, then you would imagine I'd have if I go with the NO2 as a green dots, actually let's make them the red dots because they're the bad things. So I have my NO2 right here, and in this case my N2O4 is down at 0. So if I continue to simply plot this data, you'll see the trend. So there I've plotted the points for the NO2, that's the smog. Let me go ahead and plot the points for the N2O4. And then you can see the green dots, which represent the change in the amount of N2O4. And then I just connect all the points with smooth curves here. You can see that clearly where both of these lines plateau, that's where equilibrium has reached. So the green line is where equilibrium has been reached for N2O4, and the red line for where equilibrium has been reached for the smog. You need to get used to seeing these graphs as well as understanding how these data tables are indicating the equilibrium situation. And I'm going to stop right there. Bye.